3, 2, 1, go. We're live. This is Retrace segment number 84 for Friday, December 16th, 2022 at 10 p.m. Eastern, 7 p.m. Pacific. Retrace is about what's going on out there. The short answer to that is computer control. Hence, we'll be doing computer control today, as we've been doing. The long answer to that is strategic, artificial, and natural intelligence, humanity. Retrace is about what's going on out there, and Retrace is for outsiders, and Retrace has discovered some things about the computer control game, specifically that it's player-oriented and outsiders are not players. Something like that. It's kind of sticking in my memory. The spiel, not shtick, spiel. All right, listen. We're working on, this is the December to Remember Math and Code event in preparation for the 6-month deep dive into AIMA4e, Artificial Intelligence Modern Approach, 4th edition. We're just doing math and code. We're not focused on the AI of what we're doing. We're just making sure that we can code when we need to code and code what we need to code. Let's have a look at what we need to code, shall we? Okay, so this is from Retraice 82 notes, and just the problem we're working on just for the purposes of coding, not for learning the algorithm itself or really absorbing it, the AI side of the content here, is we're trying to get from A to B. We're in Romania, and we're trying to get from Arad to Bucharesti. Listen to that pronunciation. He sounds like he's doing it right. He must be doing it right if he does it like that, right? We want to get from A to B. Our program, our agent program, is, when we finish building it, is going to solve that problem for us. Which way to go first? You've got 3 options, and then you've got 2, and then you've got, okay, what's the best way? Well, we're going to build a best first search based agent program, which is going to take 2 arguments, a problem and an evaluation function that will order our list of nodes. Yesterday, we talked about what this problem is in theory and in code. Today, we're going to talk about what this node is in theory and in code. Why are we going to do that? What you just saw is this graph is a representation of the state space that we can be in when we're trying to solve a search problem. We can be in any one of a number of states. Sometimes it's infinitely many states. In this case, it's about 24. This is the state space, and as we move through the state space, as we're solving the problem, we're going to be drawing something that kind of looks like a tree that has branches through the state space. So the maroon here, this is from the AIMA4e figures. This maroon part is the search tree. So it's important to distinguish, as they mention in AIMA, to distinguish between the search space, which you should imagine as being much more vast than your actual the state space, which you should imagine being much more vast than your search tree. State space is all the states you could be in. Search tree is the set of paths that you're going to explore and trying to get from the initial state to the goal state. Okay? That's just some theory. That's just some how to think about it. From yesterday, quickly, I just wanted to, this is the Retrace notes for Re84. This is the code we did yesterday in the terminal, but I invert the colors so that it's printable, because otherwise you'd have a big black terminal thing here and no one would be able to print the document if they wanted to. But I said a couple of times that the name of the, so we were instantiating a problem, and we were like P1 was the name that we were giving to our object, the instance of problem. That corresponds to the word self here, not the word object. I had over here in the notes, and I think I said once or twice that P1 corresponded to the word to this value object. This is not okay. So P1, the name of your particular object, corresponds to the word self in this code. This is the parent class of problem. Problem is inheriting the attributes and properties and methods of the object parent class, which we didn't talk about here, which is a more general class. I think it's a Python-defined class. So classes inherit properties and attributes and methods from their parents. I think they inherit their attributes, but they definitely inherit most of their structure. So anyway, this is all cleaned up, and I made the little explanation here, and I put it in the notes of the YouTube video as well. All right. then we're over here. We're at the GitHub, the AIMA4e source code on GitHub. This is the particular section we're going to be working on today. And now let's talk about nodes. So search space of dots, just picture them as dots. Branching tree of, I keep saying search space, state space of dots, search tree, search path, branching search path through the state space, search path through the state space, search path through the state. I gotta get that. Okay. Well, each one of these, what are the two components of a search tree, a search path through the state space? You've got little dots and little lines. Okay, the dots are nodes. The lines, you can call them edges or links or whatever you want to call them, but let's call them nodes and edges. The nodes correspond to states in the state space, but they more technically correspond to a unique path through the state space. Okay, so you can have more than one node pointing to a state in the state space. It's very mathematical. It's kind of, you gotta think here. It's function in one direction, not the other. And so what you should think of when you think of a node is not a state. It's the node. Part of what the node is the state, but the node has other attributes, other components, other attributes, and similarly, different nodes can have as one of their attributes the same state. Okay, so like, what does this mean concretely? So let's go look at the state space. Yeah, oh man, I'm gun shy about saying it now. The state space of gray boxes here, and then if we were to do a search path through it, we would see a search tree through the state space. One of these three, each of those is a search tree. Now you can have so once you reach. Let's just say you get from A to B going this short path here. Okay, this is a node, but this node has a parent, and that parent is either that thing or that thing, and it has a total cost, and that's either the total cost of going this way or the total cost of going that way. That means each of these, each of these lines that we would superimpose on this state space, the graph of this state space, can both end in a node, and so that node is not, or that state doesn't have just one node, is what I'm trying to say. The Bucharest, being in the state of being in Bucharest, so that the state of, the goal state of being in Bucharest can have two different nodes that correspond to it, one that goes this way and one that goes this way. Although these don't look like nodes, these look like lines that I'm tracing here, but the node carries all this information in it, or it carries some of the information. It carries the parent name, and then it carries the total cost, and and what else? It carries the state that it's in, the parent, the action that was applied to the parent to get to it, and then the total cost. So I think, in this case, the action is always, maybe the action is very simple when you're traveling here, just drive, but the more important thing is the cost. But if we were going, the action applied at Pitesti, what is it, Pitesti, was to go, go left instead of right, maybe, is the action that would be recorded in the node corresponding to Bucharest if you came from Pitesti. Got it? I know it's kind of confusing, but the reason that you have to understand all this is because in order to code this, every single thing I just described has to be coded. So we have to have some sense of what we're coding. Otherwise, it's just not, you're not going to be able to follow it. So each node, again, has a state that it corresponds to, and a state can have more than one node, but a node cannot have more than one state. It has a parent, and it has an action that was applied to the parent, and then it has the total cost from the initial state to the present state. And the total cost, these three are kind of easy to understand. Where are you? Where'd you come from? How'd you get from there to here? But the path cost is the one that helps us decide when we're evaluating the search, when we're expanding nodes and looking at where to go next, is the before we execute the action, we calculate the path cost to decide whether to go left or to go right. So if we're at Pitesti here, let's say we're at Sibiu here, and we calculate, and we're doing best first search. So we're going to say, which way is the best way to go? Well, first we're going to look at Fagarash, and we're going to say, oh, that's longer. So we're just going to pick the best one first. So we're going to go to, I can't pronounce these, RV, okay? We need the total cost of, why do we need the total cost? Because when we've got 3 nodes, or let's say 2 nodes to expand, so we're in like this state here, you're going to need to be able to, when your search tree only reaches to here, let's say you're at this stage of the search tree, you've got to calculate the total cost between different directions to see if, I don't know what I'm talking about. Anyway, I'm going to just spend another 90 seconds trying to say it correctly, and I'm going to get it wrong. I'm not trying to prove that I know the AI. I don't know it. That's why I'm studying it. But the code we need to do. Okay, so let's do the frickin' code. Okay, there's my little thing over here. You don't need to see that. Here we go. Okay, so I copied over the source code. We're doing basically the same sort of thing that we've been doing. Up here is this document is our note sheet. Okay, there's nothing going on up here. It's not a note sheet. It's a Python file, and we could run it down here. But down here is where we're going to run commands, and we're going to do them in IPython. But we're also going to, at the end, prove that it does what we want it to do, even not in IPython. Okay. So again, what are we doing? We are instantiating. We want to be able to instantiate a node, like particular nodes, in order to execute our program, which involves making decisions on the basis of the properties of nodes in a search tree. So we need a class, that structures all the data that we're going to need to keep for each node, and this is it. The class is node. It inherits nothing. There's nothing here. If there was something here like object. But it's not inheriting any of those. What? Never mind. I'm not going to get into it. I don't know why the one from yesterday, the problem class, inherited from object, but there's some reason for it. But anyway, we're not inheriting from object with node, not explicitly something, a parent class called an object. Okay, initialize the thing. So here we're going to give it. When we say. Okay, so this is what it looks like to initialize. So we just go down here and we say n1 is equal to, it's going to be an instance of the class node, and we're going to give it the argument s1. Now remember, there are 4 arguments here, okay? And up here, we always see this blue one. That one is just the name, okay? That's just the name that we give it. Okay, so it's put here in the argument space, but we don't actually type it there. These are our 4 nodes. These are our 4 arguments, and they correspond to. So I said let's be in state S1. Let's say our parent was mom. Let's say the action applied to mom that got us here is and then let's say the cost of getting to where we are now is 18. Okay, that's going to be our first node. Oh, geez, what did I do? Oh, yeah, I didn't define node. Well, that would be a problem, wouldn't it? Let's do that. And that, and copy. I'm just copy pasting the hard way because I do things the hard way. All right, now let's instantiate an instance of node, or instantiate node as an object n1. Okay, now we have n1 in memory. If we just type, now we're in IPython here, so there's some things that we do in IPython that won't work outside of IPython. So I put all of these things that we're going to do in print, using the print function, so that when we run the file, they'll behave. When we run the file outside of Python, they'll behave the way we want. Oh, the other thing, but you can in IPython you don't necessarily have to pass arguments to the print function a lot. IPython will often just give you what you want. Like if I type n1 right now, it's going to give me the state. But if I do it, well, anyway, there's stuff in this list that will not work in if you just run a Python file outside of IPython, unless you run it through unless you do what I've done here, which is pass these things as arguments to the print, so it prints to the standard output. Okay. The other thing that I have done is I'm not using I'm not using a virtual environment. I know I said that that's best, that's a good practice, a good habit to be in, and it is. I learned it from working on building the website. I haven't finished building the website. We're working on that, and it's a long-term project. It's good for that, but for little stuff like this, it's totally unnecessary. Certainly, it's unnecessary if you're not importing other people's code, which you're always doing that to some extent. But if you're not explicitly importing stuff, the other thing is that these little these virtual environments were kind of big, like they many dozens of megabytes, and they were doing nothing. So I deleted them from the source, and just understand that I put some notes in the source code that's up on GitHub, and the code we're looking at here will talk about virtual environments, which you should use if you're ever doing a project that you care about. But if you're doing little toy things like this, it's not necessary. Okay, not that. There we go. All right. So we've defined the class node, copied and pasted it into IPython. We put it in memory. It's in memory now, and it's part of our computer's state, voltage state. And we've also instantiated that class by defining n1 as a node, an instance of the class node. The object n1 is an instance of the class node with the state of S1, the parent of mom, the action of and the path cost of 18. That's what we're looking at here. So let's do some things to interact to see what we can see. Pint is not defined. Well, why wouldn't it be? All right, print is probably defined. Okay, so it prints when we pass our n1 object, our node object to the Python print function. I don't know. There's no string here, so I guess it's doing this. It's doing this represent or yeah. Well, you could change that behavior, but I'm pretty sure that's what it's printing when because if we had defined like we did previously, if we define string here, the magic these are called magic methods, by the way, not special methods. You can call them dunder methods. I like that better. Double under is dunder methods, but let's call them magic methods. If we defined a magic, should we just do it? I don't want to do it because then I'm going to spend too much time missing a character and waste your time. But if we define a magic method string str in our node, then it would print whatever we told it to print there. But I think the print function, this thing we just did, looks next for the repra magic method, which we've defined up here to take the state of the object. So the self.state is the argument that we gave when we instantiated the class. It's this thing here. Okay, it's in state S1. So that's what it's getting when we ask it to print this object. It's getting that S1 because of this suite right here. Okay, let's print. We're just going to use good form here because I'm pretty sure this is how you're supposed to be doing it. Whoops. Dict. Actually, is that the? Yeah, that's the way we're going to do it. Has no attribute. Do we? Oh, what do I do here? Darn it! I've done this. Oh, I missed an underscore. Okay, so there's our dictionary of stuff. It's got our state. Yeah, state. It's a key value. It's key value pairs. So we've got state is S1. Oh, geez, and parent is mom, and action is and path cost is 18. Okay, so that we've looked at the dictionary now, and that's up here. That's this line. So we've just added to our. Oh, and now the other thing is like, what about that dictionary? So if we go to up here, you can see all attributes and values. You can't see properties. You can see, and I'm not going to explain properties, but they're slightly different from attributes in object-oriented. So that's what I just did. I just did, I want to see. I'm telling Python or IPython to print the dictionary of this object so I can see all attributes and values. Now let's do dir. The dir function on S1 N1 gives us a whole bunch of stuff. I'm just going to switch screens here for a second so you can see. This is a whole list of the, don't do that, don't do that. Oh, don't do that. Oh, don't do that. Okay, we'll do that. These are all the attributes. So first we've got attributes here down here, action. It doesn't tell us their values. Action, parent, path, cost, state. Those are our attributes. And then all of these magic methods, okay? And we haven't defined any other methods. I think otherwise there would be a method in that list. Okay, just flip the screens back. Sorry if that's a little bit disorienting, but you'll get used to it. Okay, so that tells us about every method that's defined here, and every attribute that we set that we define or set. What do you say? Do you set an attribute up here when we instantiated the object? And we talked about the represent or represent. This is similar to the string. Very similar to the string method. Like I read somewhere that represent is more for, I think it's short for represent. You could also read it as short for reproduce, but I think in the Python documentation it's short for represent. The repra magic method is more for programmers, and the string magic method str is more for end users, is the way that I read one person explain it. Okay, length. Okay, so what are we doing here? We're going to find the length of, first of all, let's just see what it does. Print n1 dot, does this work? I don't know if this is going to work. Yeah, okay. No, we're going to, what are we going to do? What did I do with this? I did print, oh yeah, I did this right here. Okay. So let's print the length of our two. We've only got one object, so I'm only going to be able to print one of these. And that's 4. That's kind of interesting. It's not really, because the length that that's interesting to us is the cost, the total cost. This is like the, no, it's not the total cost. What is the length for? Crap, I don't remember. If the parent is none, return 0, else add 1 to the parent. We're going to use this later for like the number of steps or something. That's what this is keeping track of. It's like how many nodes. But I don't think that that's part of our essential list of things that need to be in this. Let's have a look here. Let's go back to our essential list over here in Re84 live notes. So path to cost, path cost, action applied. Yeah, that's not in our essential list. So we don't need length, but we're going to need it later. They wrote this code, so they but there's no comments that explain what that's for. But you can see what it does. Like if we print the length of n1, it's 4. If we print the length of n1.parent, it's 3. So what is that? What is that 3? What is it counting? Okay, it's counting the number of letters in the word mom. Okay, that's my understanding of that. So so that's what you're seeing there. Why we need that, and that also means like when we give parent here, when we instantiated the object, the class as this object, when we gave this parent, I'm just giving strings just to illustrate, but this should be some sort of number. The parent should be a number if the length is going to have meaning, but I don't know. Okay, I just don't know that one. We'll see later as we get more involved in the implementation. Okay, last but not least, the less than magic method. LT stands for less than. So it's basically going to tell the computer what to do when greater than or less than function or operator is applied to our object. And what that looks like is, let's say let's define another object. Right here. Oops. No. What am I doing? Where did I go? Oh, yeah, right there. Okay, so now we have two objects. Sorry, two nodes which are objects. So one is in state 1, one is in state 2. You can see there. So again, I instantiated the class node as the object N2. I gave it first this argument, which is the state that it's in, then the parent, I said the parent is nature, and then the action that came from is evolution, and then it's 2 billion years old. Okay? That's what's going on there. Now let's compare the two. Let's go print, not pint, print, what is it, N1? Why is it not auto-completing? There we go. Okay. And so so I'm asking IPython to tell me whether to compare these two using the greater than operator, and less than works the same way. And this suite is telling Python what to compare. This node is a big complicated thing, right? Like an instance of this node is a big complicated thing. If I just say, hey, is it greater than or less than, and is N1 greater than N2? What greater than it is the total number of characters in the, or the space it takes up in memory or whatever. No. This is we're defining this magic method to take the thing itself, okay, and then the other, and return the path cost of the self, and or to compare the path cost of the self and the path cost of the other. Okay, and both of them have path costs. What are the path costs? One was 18. So the path cost of N1 was 18. And then the path cost of N2 was 2 billion. And so what I asked here is 18 greater than 2 billion? And the answer is no. And we can somewhat, increase our confidence here if we ask the same question again in the other direction. Is 2 billion greater than 18, or is 18 less than 2 billion? Okay, so these are the aspects, or the elements, or the methods and attributes of our nodes, which are going to be instantiated from the class node. Okay, that's what we're going to use when that's the code. That's the structure of the code that we're going to use when we do nodes. There's more stuff to do, but we're getting there. I just did something terrible. Oh, check this out. This is terrible. What did I press? I was doing no. Don't want that. Go away. And one more thing. So I've got, just like I said, you don't have to do this in IPython. Let's do Python, and there we go. Now we can switch these. So I just ran the same file and all the things we did, because they're not commented out. Come on. And so these are all the outputs from those those functions, those print functions. We printed the thing itself. We printed its oh no, I don't remember. We printed the dir function on N1. We printed the dictionary of N1, and then we printed the length of N1 and the length of N1's parent, and then the length of N1 and N2. Remember, these are the ones that are counting the length of the name, mom, and then nature. N-A-T-U-R. N-A-T-U-R-E. And the reason it's 7 and not 6 is because you add 1. Because remember, this is confusing. Up here, the length of the object is the length of its parent, nature, 6 letters, plus 1. Okay, so that's that. And then we printed the path costs of the two, and then we compared them and said, is 18 greater than 2000? Right? Is that what we said? Yeah. Okay. So that's it. All notes and code will be in the PDF notes at retraice.com, retraice.com. Also, you should be able to click to them from wherever you're watching or listening to this, and see all that good stuff. And we'll do the same. We'll do more on implementing the best first search program algorithm in the form of an agent program and the agent function. What's the agent function? I think it's that evaluation function. That's the agent function. That's the thing that makes the difference in that agent. But I don't know yet, because we're not focused on the AI stuff. We're focused on the code. All right, fun and games, good. Same time tomorrow, 10 p.m. This has been Retrace segment number 84. Signing off.